All right, welcome to section 4.2, where we're going to continue our discussion with probability. And as I stated in the last section, probability can be a little bit confusing, so I suggest that you go and take a look at the practice problems that are available to you. And the more that you practice the probability questions, honestly, the better you'll get at them, and the more confident you'll be in answering the questions. Okay, so in this section, we are going to calculate and interpret conditional probabilities. We are going to use the general multiplication rule to calculate probabilities, and this is going to be your AND rule. In the last section, we looked at the addition rule, which was used for OR. We're going to use tree diagrams to model a chance process and calculate the probabilities using two or more events. This is going to be one of the most important sections, is whenever we are given conditional probabilities, you're going to want to get used to that tree diagram. It makes finding the answer so much easier. We're going to determine if two events are independent and when appropriate. We're going to use the multiplication rule for independent events to compute probabilities, and that's going to be involving the tree diagram that we're going to take a look at earlier. So what exactly is conditional probability? So we briefly took a look at it in the last section. So it's the probability that we assign to event if we know that some other event has already occurred. So this is the key to many applications of probability. So given that it rained on Tuesday, what is the probability that it's going to rain on Wednesday? Given that we are looking at the male population, what's the probability that they have pierced ears? Given that we're looking at the female population, what is the probability that they have blonde hair? Okay, so conditional probability means you're already given a specific condition, so you're ruling out a bunch of possibilities. So when we're trying to find the probability that one event will happen under the condition that some event is already known, we determine this is a conditional probability. We put a condition on it. We're only looking at males. We're only looking at females. So the probability that one event happens given that another event is already known to have happened is conditional probability. So let's just suppose we know that event A has happened. Let's suppose that we know we're just looking at the population of males. Then the probability that event B happens given that A happens, so the probability that we find someone with pierced ears knowing that they're male is denoted by B with this little line A. So this is read as B given A. A is already known. Okay, we already know that we're just looking at the population of males. Find the probability of B given that A has occurred. Okay, so knowing that A has occurred often changes our probability answer or our answer. Okay, so just make sure you understand that it's read as given that under the conditions that, B given A, B under the conditions that, but most of the time you'll just read as B given A. Look at how conditional probability will apply to the example from section 4.1. In section 4.1, we took a look at a bunch of people that were either high school graduates or homeowners. All right, so let's just take a look and see how we can apply conditional probability to this situation. Let's say we know that a person owns a home. All right, so that means the condition is that they're a homeowner. We're only looking at the row where they are a homeowner. What is the probability that the person is a high school graduate? So here's what we know. We know that there are a total of 340 people in the sample who own a home. Because 221 are high school graduates, here's our probability. The probability that you're a high school graduate given that you own a home, all right, so here's the high school graduates, it's 221, over the total of the home is 340, or 65%. So understand that the given is kind of like your denominator, given that you own a home. The homeowners is the denominator since it was given. Okay, so the key to conditional probability is just understanding what you're given. That becomes the denominator. All right, so in symbols, it would look like the probability of G given H. The probability that they graduated from high school given that they were a homeowner. Okay, so let's just continue taking a look at this example. Let's say that we know that a person is a high school graduate. Now we're ignoring anything that is not a high school graduate. High school graduate is basically now our denominator. So knowing that the person is a high school graduate, we're getting rid of everything else in the table. What's the probability that the person owns a home? So there are a total of 310 people who are high school graduates. Because 221 are homeowners among the 310, the desired probability is the following. Okay, so if we take a look at our table, so in the last column, it was given that they were a homeowner. So we already knew that they were a homeowner, so we were crossing everything else out. In this case, we are given that they're a high school graduate. So we're essentially getting rid of everybody that's not a high school graduate. All right, so what's the probability that they own a home given they're a high school graduate? All right, so take a look. Our new denominator is high school graduate because that's the only group of people that we're looking at. So there's your 310, the total of 310. What's the probability that they're a homeowner? There's your 221. So 221 out of 310, or 0.71. Just once again, please remember that you need to show the probability statement, the fraction, and your decimal answer. In symbols, we could write the probability of H given G, homeowner, given that they're a high school graduate. Okay, just make sure if you do H given G that you define what H is and you define what G is, which we actually did on the previous slides. Okay, so let's just take a look at the example and figure out how we can calculate conditional probability. It's easy from a table because all the numbers and data are laid out right before you. All right, so we looked at the probability that they owned a home given that they were a high school graduate. So from the table, we could very easily just cross out the fact that they were not a high school graduate and just look at the information here. All right, so what exactly did that probability look like? What did the 221 and the 310 represent? So the probability that they own a home given that they are a graduate, the numerator of 221, if we look on our table, was the probability that it was the number of homeowners and the fact that they were a graduate. It was the intersection of the two. So the top was A and B, home and graduate. Take a look at the denominator of 310. Well, the 310 was the fact that they were a high school graduate. What did that come from? That came from the conditional probability. Okay, so what if we decided to write this as a probability instead of just using the numbers from our table? All right, so we already said that the conditional probability of owning a home given that they were a graduate is the probability. Okay, so let's just take a look at that probability. Owns a home given that they were a graduate. The numerator was the fact that they were the probability that they were a homeowner and a graduate. So where can I find that on my table? What's the probability that they're a homeowner and a graduate? We'll take a look. The probability that they're a homeowner and a graduate is 221 out of the total of 500. That's just the probability of homeowner and graduate. All right, take a look at the bottom. So the bottom was the number of the high school graduate, but what's the probability that they're a graduate? The probability that they're a graduate is 310 out of the total of 500. So if we take a look at the probabilities that you're a homeowner and a graduate, 221 out of 500, all divided by the probability that they are a graduate is 310 out of 500 equals 221 over 310, which is the same as the probability that we got straight from the table. Basically, the denominators of 500 cancel each other out. So this is the same answer that we arrived at previously. This probability will lead us to a general formula for computing conditional probability. So this formula right here. So keep in mind, it's the probability of both occurring divided by the probability of what you were already given. We calculate conditional probabilities. So the probability of A given B is using the following formula. A given B, the numerator, just like it was in the previous problem, is the probability of A and B divided by what was already given. So divided by the probability of B. So think about B, or what's given, is always going to be your denominator. So this is the same formula that we derived on the previous page. So what happens if we have the probability of B given A? All right, it's the exact same formula. The numerator is still the probability of both occurring, all divided by the probability that was given. So in this case, what was given, A was given. So don't try to memorize the formulas specifically. Just remember when you have a conditional probability that the numerator is always the probability of both events occurring, the and probability, and the denominator is always the probability of what you're given. So given is your denominator. It's a great denominator because it's already given to you. Is on the AP exam formula sheet. So this is the version that you'll see on the AP exam formula sheet. So just keep in mind though, it's just telling you that for a conditional probability, A and B, it's the probability of A and B to get divided by the probability of B, or essentially divided by what is given. So the denominator is great, it's what's given. Okay, so what work do you need to show? Okay, you must show the probability statement. So this statement right here, A given B, high school graduate given that they're a homeowner, something like that, and the numbers you plugged into the numerator and denominator. So you have to show the numbers for the numerator and denominator, even if they're decimals. If you do not show the decimals plugged into the numerator and denominator, you will be marked incorrect. Okay, so if this is like 0.25 divided by 0.16, still show that. Okay, I know it's sort of funky to put decimals in, but still show your work. Does it matter which formula you use? Absolutely not. So just remember this, the probability of A given B or anything is the probability that the both events occur, the and probability divided by the probability of what is given. Okay, just remember that when you're writing out the probability statement, the trickiest part is to make sure you have the correct portion after the given. So when you read the question, you're going to have to carefully read it to understand what portion is given. Okay, and then that goes in your denominator. Okay, so what I'd like you to do is just take a minute and try this question on your own. So the students at University of New Harmony received 10,000 course grades last semester. This two-way table breaks down these grades by which school the university taught. All right, so here is the different schools: liberal arts, engineering and physical sciences, health and human services, and here's the grades that they received: A, B, or below a B. E is the grade coming from the engineering and physical science course, and L is the fact that the grade is lower than a B. All right, so what I would like you guys to do is try to find these three probabilities. Take a minute, pause it, see if you understood what this notation means, and then we'll check our answers. Okay, so number one, the first thing that you should have done, hopefully you remembered, was find all of the totals. It is much easier once you found the totals. All right, so the probability of L is the fact that the grade is lower than a B. All right, so if we're looking at this section right here, so here's lower than a B divided by my total. So that's why it's important to find the totals. Find the probability that the grade comes from an engineering and physical science course given that it's lower than a B. So from the table, it's easy to see, okay, our new denominator is now just given the fact that it's below a B. So I don't even need anything from the A or B section, okay? So the probability that our engineering and lower than a B, that's your 800, okay, divided by just below a B, because that's what we're given from the table, okay? Take a look at the last one. Find the probability that it's lower and they're from engineering, or sorry, given that they're engineering. So if you take a look, given the fact that it's lower than a B, find that it's lower than a B, given that they're from engineering. Now engineering is now our denominator. So we're essentially crossing out all of the other rows. Okay, so what's the probability that it's lower than a B and engineering? That's still your 800. Given that they came from the engineering department, which is your 1600, that's your new denominator. So remember, what's given is always your denominator because you're crossing out all the other possibilities. Okay, so let's just take a minute and decide what exactly do these conditional probabilities tell us. So further information that we have collected, we know that college grads tend to be lower in engineering and the physical sciences than in liberal arts and the social sciences. This is interesting, and I'm sure you'll be looking into this as you go to school. You'll just sort of notice that the engineering and the science majors just tend to have a lower grade average overall. Which one of the conditional probabilities tells you whether the college EPS students, which is the engineering and physical science students, tend to earn lower grades than students in liberal arts and social sciences. Okay, so we can use conditional probabilities in order to answer this question. So just take a minute, and before we go over the answer, think about which of the conditional probabilities will tell us this. Okay, so let's just take a look at the grades lower than a B. Okay, let's take a look basically at the percentage or the probability of students that are in liberal arts or engineering and physical sciences. Let's take a look at those probabilities or percentages given the fact that they have lower than a B. All right, so let's first find the probability that the grade is from engineering given that the grade is lower than a B. Now remember that you should have found the totals, okay? So the totals of grade lower than a B were 3,656, okay? Now we're just going to look at the engineering and physical sciences from that column. That was 0.2188, okay? Let's then look at the conditional probability, all right? What is the probability that you get lower than a B given that it's a grade from engineering and physical sciences? Okay, so we're given that it's a grade from engineering and physical sciences, and that's that total right here. That's at 1,600. Okay, where's the intersection that you're lower from a B and engineering and physical science? That's this right here. This is your 800. Okay, so that's the 800 over 1,600. Now, what do these two probabilities tell us? These are hugely different. Knowing that it's from engineering and physical science, what's the probability that it's lower than a B? That's 0.5. But given that it's lower than a B, what's the probability that it's from engineering and physical sciences? That's only 0.2188. So what do these two probabilities together tell us? If we take a look at the second one, the probability that we're lower than a B, given that the grade was from engineering and physical sciences, gives the probability of getting a grade, a lower grade, given that the student is studying engineering or physical science. Because this probability, which is 0.5, is greater than the probability of the fact that you are from liberal arts school, which is 0.3656, we can conclude that the graders are lower in engineering than in physical sciences. So basically this is telling us that almost 50% of the grades that are lower than a B are from engineering and physical sciences. Work will you need to show for the AP exam? So previously we classified houses by the type of phone that they had in their home. All right, that was a previous question. Remember, we talked about landline, no landline, cell phone, no cell phone. Given the below table, what's the probability that a randomly selected household with a landline also has a cell phone? All right, so go ahead, take a couple seconds, see if you can answer that question. Just keep in mind, I have the totals here. You would want to make sure you include those if they are not already there. Okay, notice the total here is 1 because we're talking about probabilities. See if you can write out the probability statement. Okay, so here's the question. Did you get the conditional probability statement correct? All right, we want to find the probability that you have a cell phone given that you had a landline. So this is the tricky part. So if you read this again, given that the below table, what is the probability that a randomly selected house with a landline? So that's what we already know. We already know that it has a landline. All right, so that's your given probability. Also has a cell phone. So we want to find the probability that you have a cell phone given that you have a landline. So using our conditional probability formula, all right, we want to first find the probability of cell phone and landline. So there's your 0.51 right there over the probability of a landline, which is your 0.60. Okay. So on the AP exam, the work you would need to show is this conditional probability right here, this statement, this decimal fraction, and then your simplified fraction as your answer, or obviously you can't ever report a final answer as a decimal over a decimal, so just divide it to get that final answer. Okay, so work needs to be shown. Probability formula with correct notation. Make sure that you have the given portion correct, because if you have given cell phone but then have the correct work over here, it's going to be marked incorrect. All right, so just keep that in mind. All right, your fraction with your decimals filled in right here, and then your decimal answer. And just keep in mind with conditional probability questions, it usually doesn't say, given that you have a household with a landline, what is the probability that they also have a cell phone? All right, so you're going to kind of look out for those trick words. If a question is asking for conditional probability, especially if the question doesn't say given that. So will the question always state given that? No. Even in the, take a look at that last example, it didn't say given that you had a landline. It's never going to be that easy. So here are some other words to look for in order to recognize that you're dealing with conditional probability. So who has a landline? All right. Whose house has a landline? Find the probability of a cell phone. Which house has a landline? Then find the probability of a cell phone if they have a landline, and given that they have a landline. So those are 5 words that you can just take a look at that will help you understand that potentially what you're looking at is a conditional probability, and this would be the condition that's already given, so this would be your denominator. All right, so let's just take a minute. So we've talked about conditional probability. We're going to apply the general multiplication rule to the conditional probability. So what happens if we're not given a table? How do we find the probability of A and B actually occurring? Okay, so we don't have that nice little table to find the intersection. The probability that events A and B both occur can be found using the general multiplication rule. The general multiplication rule tells us the probability of A and B is the probability of A times the probability of B given A. Now let's just sort of think about this. The probability of B given A is the conditional probability that event B occurs given that A has already occurred. This is just the conditional probability formula reworked. Okay, so if we think about this, the probability of B given A is equal to the probability of A and B all over A. All right, so this is just that conditional probability formula reworked. In other words, this rule says that for both of events to occur, the first one must occur, and then given that the first event has occurred, the second event will occur. All right, so like I said, just reworking that conditional probability formula. So it's assuming that this is the first event, the second one is the second event, assuming that the first event already occurred. So this is a conditional probability. The second event, assuming that the first event already occurred. This formula is not on your AP exam formula sheet. However, the conditional probability formula is. So if you notice, the general multiplication rule, which is what we just talked about, is the conditional probability formula just rearranged, okay? So you can rearrange the conditional probability to find your and probability. Okay, so let's just take a look at an example of using our multiplication rule and what work we'd need to show for the AP exam. All right, so about 55% of high school students participate in a school athletic team at some level. This is in high school. And 5% of these athletes go on to play on a college team in the NCAA. Got a little picture right up here. What percent of high school students play a sport in high school and go on to play a sport in the NCAA? So take a minute, try this before you check your answer on the next slide. All right, so how do I answer this question using the multiplication rule, and what work would you need to show for the AP exam? And remember, what work you need to show for the AP exam is the same work you need to show for your tests and your quizzes and your homework assignments. All right, so let's look at the question. What percent of high school students play a sport in high school and go on to play a sport in the NCAA? Since this is a multiplication, since you know by the word and is telling you that's a multiplication problem, let's write out what that looks like. We want to find the probability that they play in high school, okay, and they go on to play in the NCAA. So what does that look like with our multiplication rule? So the probability that they played in high school times the probability that they play for the NCAA given that they played in high school. So your and rule says, okay, the first event occurred, the second event occurred knowing that the first event have already occurred. Okay, so we know that the probability that they play in high school is 0.55. That's given in the problem. We know that the probability that they go on to play for the NCAA, given that they went to high school, is 0.05 because the wording in the sentence said 5% of those students go on to play for the NCAA. So 5% of the students in high school, so given that they were in high school. So on the AP exam, you need to show the probability that they went to high school and played for the NCAA, these two multiplication, the 0.55 and the 0.05, and then your final answer as a decimal. Okay, and then please make sure that you write your answer as a sentence in context so they know exactly what probability you found. So 2.75% of high school students will play a sport in high school and in the NCAA. That's really not that high of a percentage. So the highlighted work is the work that you need to show for the AP exam. Let's just talk quickly about conditional probability and independence. So that multiplication rule that we just took a look at used the multiplication rule and conditional probability. Now, what does it mean to be independent? So when the knowledge of one event has happened does not change the likelihood that another event will happen, we'll say that the two events are independent. So basically that means what is the probability of rolling a dice, getting a 6, and pulling a queen out of a deck of cards? When I know the probability of rolling a dice and getting a 6, whatever number that I get on my 6, whatever number that I get on my dice is not going to affect me pulling a card out of a deck of cards. It's not going to affect the probability of me getting a queen. Those are two completely independent events. The probabilities are going to stay the same. The probability of rolling a dice and getting a 6 is going to stay the same no matter what card I pull out of my deck of cards. Okay, so two events A and B are independent if the occurrence of one event does not change the probability that the other event will happen. So, in other words, A and B are independent. So this is back to our conditional probability. If the probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B. So basically this is like saying, okay, the probability of A knowing that B occurred is still the same as the probability of A. B did not affect A at all. Over here, the probability of B given A is the same as the probability of B. This is like saying A didn't affect B at all. So the probability of B is the same no matter what. So the probability of rolling a dice and getting the 6 is exactly the same whether or not I pull a queen or a 6 out of my deck of cards. Okay, pulling a queen or 6 out of a deck of cards is not going to affect the probability of rolling a die. Okay, so when A and B are independent, we can simplify the general multiplication rule since the probability of B given A is just the probability of B. So what does that look like? So if you have independent events, this only works for independent events, the probability of A and B is the probability of A times the probability of B. Okay, so think about this. Our previous one was the probability of B given A. Okay, so we're replacing that with just the probability of B. All right, if you are asked to prove that two events are independent, there are two ways to do that. Now, do not ever just state this statement right here, this conditional probability statement. You have to show the numbers plugged in. All right, so if the probability of A given B is the same as the probability of A, and the probability of B given A is the same as the probability of B, then they're independent. All right, then they're independent. So the probability of rolling a dice and getting a 6, given that I've pulled a 6 out of a deck of cards, is still the same as the probability of rolling a dice and getting a 6. You have to show the numbers plugged in. What is the probability of A given B? What's the probability of A? Are they equal? Not equal. What's the probability of B given A? What's the probability of B? Are they equal? Not equal. Show the numbers plugged in. Now notice that we use the conditional probability to prove that the two events are independent. Why? Why does this work? the reason this proves independence is if the probability of A doesn't change with B occurring, then it means that B doesn't affect A. Therefore, they're independent. So you have to show those numbers plugged in. What's the second way to prove that they're independent? The second way to prove that they're independent is by plugging the numbers into the formula and showing that the probability of A and B is the same as the probability of A times the probability of B. If the above equation is true, then we can say the two events are independent. So if you're asked to prove independent, you can either prove it using the multiplication formula or the conditional probability formula. All right, but you have to show the numbers plugged in. You don't have to use both. Pick one. Okay. Once again, you must show the work plugged in. Don't just give the equation and state therefore independent. That's incorrect. Remember, stats is all about proving where you got your information and why it works. Here, we're just going to go over a quick example of the multiplication rule for independent events. Following the Space Shuttle Challenger disaster, so back in the 1980s, Space Shuttle Challenger went up and blew up, I think, within like 10 seconds of launching. It was determined that the failure of O-ring joints in the shuttle's booster rockets were to blame. Under cold conditions, it was estimated that the probability of an individual O-ring joint would function properly was 0.977. Okay, so there was not 100% probability that the O-ring joints would function properly under cold conditions. Okay, so we're assuming that O-ring joints succeed or fail independently. So we're assuming that they're all independent of each other. What's the probability that all 6 would function properly? Since we know they're independent, we can use our multiplication rule. So basically, we're saying what's the probability that joint 1 was okay, joint 2 was okay, joint 3 was okay, 4, 5, and 6. Okay? By the multiplication rule for independent events, all we have to do is multiply the fact that joint 1, joint 2, joint 3, joint 4, joint 5, joint 6 was all okay. So basically, it's 0.977 to the 6, okay, because they all have the same probability of success. So it's a 0.87 probability that all 6 O-rings would function properly when the rocket launched. Okay, so basically what's that telling us? There's an 87% chance that the shuttle would launch safely under similar conditions and a 13% chance that it wouldn't. Oh, yikes. Okay, so I have an interesting article on the space shuttle for this. Maybe you've taken a look at it, and actually it's later on. It will show you why it actually failed. We use tree diagrams. Now, when you are dealing with any sort of situation where you have two things going on, whether you might not know they're independent, you might know they're independent, knowing they're independent is easier. If you're not sure, I would always suggest drawing a tree diagram to answer probability questions, okay? Unless it's something that you can use with a table or a Venn diagram, draw a tree diagram. It will help you answer the questions much easier. If not, you're going to be digging for probabilities, so get used to doing this now. So the general multiplication rule is especially useful in probability when we're talking about a sequence of outcomes. So that's really like our conditional probability, having sort of two scenarios going on at one time. The best thing to do is to draw a tree diagram, list the sample space, and list the probabilities under each sample. All right, so let's think about flipping a coin twice. What's the probability of getting 2 heads? Okay. All right, this isn't too bad. Let's take a look at our sample space. If I was going to flip a coin twice, I can get 2 heads, heads and tails and heads, 2 tails. So the probability of 2 heads is heads and heads, which is 1/4 or 0.25. Okay. How can we get that probability? Using a tree diagram. Okay. So the first branch of the tree diagram tells us, okay, what's our first toss? On the first toss, I can get heads or tails. What's the probability of getting heads? 1/2, tails 1/2. On the second toss, what can happen? So on the first toss, I got heads. On the second toss, I can get heads or tails. Let's say on the first toss, I got tails. Then on the second toss, I can get heads or tails. What are the probabilities associated with getting heads, getting tails, getting heads, getting tails? 1/2 for each of them. Now, what is this 0.25 at the end of the branches? Where does that come from? That is multiplying across the branches. Now, we're assuming that these are all independent because when you flip a coin, okay, the second one, second time you flip a coin. It's not going to change. It's not based on the first one. So notice I did 1/2 times 1/2 to get the end of the branches, and that represents the probability of getting 2 heads. What's the probability of getting heads and tails? Okay, 2 heads is going to be, heads and tails is 1/2 times 1/2 to get your 0.25. Tails and heads, 1/2 times 1/2, 0.25. Tails and tails, 1/2 times 1/2 equals 0.25. So notice that end of the branches are the multiplication of the branch. Always fill those in. So we could use our sample space. Okay, it's 1 out of 4, or we can use our general multiplication rule of 1/2 times 1/2 to get us the 0.25 for the probability of 2 heads. Okay, always multiply across the branches to get the probabilities. This is going to help you significantly with conditional probability questions. About tree diagrams. Number 1, what are some properties of tree diagrams? So this is our tree diagram from tossing a coin with our first and our second toss. Okay. The first thing that you do is you draw your tree diagram, put your probabilities, multiply across to get the end of the branches. Now, what I want you to understand is the probability at the end of the branches represents your intersection. Heads and heads, heads and tails, tails and heads, tails and tails. All right. Why do I have all these plus signs here? Okay, number 1, the probability that all of the events occur is always going to be equal to 1. So the end of your branches should always add up to 1. The reason they add up to 1 is because these are all of the possibilities that could happen with 2 tosses. Okay, notice here, this is 0.25, this adds up to 1. These 2 branches add up to 1, these 2 branches add up to 1, and these 2 branches add up to 1. Okay, so keep that in mind. All right, so I'd like you to try this one. So the Pew Internet and American Life Project finds that 93% of teenagers aged 12 to 17 use the internet, and that 55% of online teens have posted a profile on a social networking site. Look at this question. What percent of teens are online and have posted a profile? Okay, so you might say, oh, I could just use the multiplication rule. Sometimes it's not going to give you the right answer if they're not independent. Anytime you get a question that has an and they have multiple things going on, so we're talking about the internet and posting a profile online, draw a tree diagram to represent all of the possibilities. Okay, so what exactly is this going to look like? Okay, number 1, let's take a look at this first probability. They find that 93% use the internet. So let's look at first, okay, 93% do use the internet, 7% don't use the internet. So are they online? Yes or no? So your tree diagram is going to represent your 2 situations, okay? Now what does it tell us next? 55% of online teens have posted a profile on a social networking site, all right? So now go to your tree diagram. Knowing this says 55% of online teens, so knowing that they're online, 55% posted a profile. So profile yes is 55%. Well, how can I figure out the percentage of students that are online that didn't post a profile? Well, remember your branches add up to 1. So you're going to do 1 minus 0.55 to get the 0.45. Okay. And then we also know this 7% is not online. So obviously they're not going to post a social networking site. And since they're not online, they're not going to post a profile. So 100% of those are basically not posting a profile because they're not online. So 0% are saying yes. Okay. All right. So how can we find out the probability? Answer this question. So what percent of teens are online and have posted a profile? So remember, we have to do probability of online and posted a profile. So what's the probability that they're online? Okay, that's what's given, the fact that it's online, okay? So then we have to decide what's the probability that they posted a profile given that they were online. So online was already given, okay? So looking at our tree diagram, here's how we can answer this. The probability that they were online and have a profile is the probability that they're online, so the probability of A, times the probability of A given B. Okay, so since we already know that they are online, that has to be our given portion, the probability that they have a profile given that they were online. Okay, so that's your 0.93 times your 0.55. Okay, and if you take a look at the end of that branch, that's what it would be. Okay, knowing that they're online, what's their profile? Okay, so 51.15% of teens are online and have posted a profile. So we can multiply this. We can get this by multiplying the ends of the branches. This will always represent the and portion. So the end of the branches are always going to be your and portion. Guys, honestly, are just going to be a bunch of practice problems that represent everything we've learned in this section. So they're independence, tree diagrams, the multiplication rule, and conditional probability. The best way to get better at these questions is just to try them. So as we go through these, I'm going to present the question, I'm going to let you guys read it, and then I'll go over the answer. So if you need to pause it as you're looking through the slides, go ahead and pause it, try the question, and then take a look at the explanation. Okay, so hopefully this one was a little bit easier since everything was given to us in our table. Okay, so in our table, we know that it's the probability of A that the student has allergies. All right, so if we take a look at across our table, this would be allergies, so that would be 18, just that they have allergies, so over the total, which is 40. So 18 over 40, which is 0.45. Now, letter B says find the probability of A given F, so that the student has allergies given that they're a female, and the probability that they're a female given that they have allergies. So if we're looking at the fact that they have allergies given that they're female, okay, basically we're just looking at the female column. Okay, so right here, this is our new total. So that total is 23. Where's the intersection of female and allergies? That's your 10 right there. So 10 out of 23, which is 0.434. Okay, all right, now take a look at the probability of F given A. So what's the probability that you're a female given that you have allergies? So what's the denominator here? We know that we have allergies, so we're just looking at the allergies row of 18 as our denominator. So how many of those are females and allergies? That's your 10, which gives you 0.55. Okay, and the allergies column is your denominator. Now, let's just take a look at the next question with the allergies. So we took a look at independent events. Are events A and F independent? How do I know? But please remember that the way this question is answered is how you will need to show the work anytime you're asked to prove independence. You have to show your work. You can't just say the probability of A is equal to A given F and the probability of F is equal to F given A. All right, you have to show all of the parts. All right, in order for them to be independent, we're checking to see if A and F are independent. So in order for them to be independent, you have to answer the question, is the probability of A the same as the probability of A given F? So what is the probability that the student had allergies? So that was your 10 out of your total, which was 40, which was 0.45. What's the probability of A given F? So remember we know that they're females. The probability that they had allergies was 10 over the female of 23. That was 0.434 from the previous slide. Now, notice how I showed the probabilities, showed the formula, showed the numbers plugged in. Okay, those two are not equal. Since they are not equal, they are not independent. Being a female does affect the probability of having allergies. Okay, so taking a look at these questions, how exactly do I know when I'm moving on? When do I know to use a tree diagram? Or how do I know to use a two-way table like the one we just looked at? Number one, anytime you're given conditional probability. So anytime you're given two things that are happening, anytime that you're given, remember those words, those 5 words, whose, if, given, use a tree diagram. It's going to make it so much easier. It is very difficult to do conditional probability without a tree diagram. Okay, you're going to use a two-way table when you're given counts. Make sure to put them in a table. Make sure to get the total in the table column. Okay. All right, so go ahead, take a minute, read this question. Okay, and then we'll go over the answer. Okay, so hopefully as you started answering this question, you recognize the fact that you wanted to use a tree diagram since there's conditional distributions. Well, how did you know that there was conditional distributions? All right, take a look at the question. 17% were light media users, 62% were moderate, 21% were classified as heavy. Now, notice how the question says, of the light users who responded, 74% describe their grades as good. That's a conditional distribution or a conditional probability right there. Of the light users who responded, 74% were good grades. Okay, so of the light users, that's given to you already. Now take a look at the second one. 68% of the moderate users, that was given to you. So that indicates conditional probability. And 52% of the heavy users described their grades as good. That was given to you. According to the study, what percent of young people ages 8 to 18 described their grades as good? Anytime you see two things going on, draw a tree diagram since we're talking about conditional distributions or conditional probabilities. Now, the tricky part is deciding from the question, what is your given statement? Before you even try to answer this question, draw the tree diagram. Okay, so let's see what that looks like. Number one, what we started out with was this first portion had no conditions on it. So 17% were light users, 62% were medium, and 21% were heavy. This should all add up to 1. All right, then we knew of the light users, 74% described their grades as good. So good grades is 74%. Since these two add up to 100, we can figure out not good grades. All right. Of the moderate users, they said 68% were good grades. Add those two up. They have to equal 1. So you know not good grades was 0.32. Then they told us that 52% of heavy internet users said they had good grades. This has to add up to 1. So not good grades was 48%. Always make sure when you draw your tree diagram to put the probabilities at the end of the branch. So multiply across light good grades, light not good grades, medium good grades, medium not good grades, heavy good grades, heavy not good grades. How do you know whether or not you did this correctly? Remember, this all has to add up to 1 because that's 100% of my probabilities. All right, so that's just a quick way to check to make sure you did that correctly. All right, so now how are we going to answer that question? So we have all of our possible probabilities. Now we want to find what percent of young people ages 8 to 18 describe their grades as good. So where on here are describing their grades as good? So I have 3 different columns where I have good grades. I have light and good grades, medium and good grades, and heavy and good grades. So I want to add up those 3 probabilities from the end of the branches. All right, so this is an and question. All right, so I'm just adding up the 3 probabilities. All right, so keep that in mind. This is where the tree diagram will significantly help. If you didn't have that tree diagram, it would be difficult to tell, oh, okay, look, there's 3 columns here, or 3 different sections where I have good grades. Heavy, medium, and light. So anytime you have 2 or more things going on, draw a tree diagram, then answer the question. Okay, so let's take a look at the second question. What percent of students with good grades are heavy users of media? All right, so now this question is a little bit different. What percent of students with good grades are heavy media users? Now notice this says with good grades. So we already know that they have good grades. So since we already know that they have good grades, that's our given. So when I write my sentence, okay, so this is recognizing that this is a conditional probability. What's the percentage that they're or the probability that they're heavy media users given that they have good grades. So when I write out this probability, okay, the probability that they are heavy users of media and they have good grades over the probability of getting good grades. Now, what's the probability that they're a heavy media user and they get good grades? Very easy to find from my tree diagrams. See how important this is? This baby's awesome. It's going to help us figure out everything without any work or confusion. Okay, boom, right here. There's your intersection. That's this point right here. Now, what's the probability that they get good grades? Well, that might be kind of hard to find if I didn't have that tree diagram, because there's 3 separate parts where they get good grades. So the numbers in the red box are the numbers of the probability of getting good grades. So you're adding all of those up in your denominator to get the probability of good grades. So heavy and good grades divided by good grades equals 0.166. Okay, show this work right here and then your final answer. So about 17% of young people who say they have good grades are heavy users of media. Okay, so we're assuming that they have good grades. That's our given. So much easier to do with a tree diagram. Please start making them early. When I first started doing probability many moons ago, and I did not do this, it was very difficult and very confusing. So if you're having trouble, draw the tree diagrams. Okay, so go ahead, take a minute and read this one. Okay, so in this case, we didn't need to draw a tree diagram. I didn't have 2 things going on. I only had 1 percentage or 1 probability, is the fact that a perfect inning happens only 40% of the time. There's no other conditions happening, so you don't need a tree diagram, especially since they're all independent events. So since they're all independent events, I can just use the multiplication rule. All right, so the question was, what's the probability that a pitcher throws 9 perfect innings in a row? So that's like saying I have no hitters for 9 innings. So perfect inning 1, perfect inning 2, 3, 4, 5, 6, 7, 8, 9. So the probability of no hitters for 9 innings is 0.4 raised to the 9th, or 0.49 times, which is 0.0026. So what work do you need to show for the AP exam? Make sure you show your probability and then your final answer. I would also include putting the 0.4 to the 9th. Okay, so go ahead and take a minute and read this one. Okay, so this one's a little bit tricky. So the question says, among 100 women with normal pregnancies, what is the probability that there will be at least one false positive? Now, this strategy that I'm using for this question only works when you have at least one. So, because if not, okay, so among 100 women with normal pregnancies, what's the probability that at least one will be false positive? So I'd have to add up the probability of 1 false positive, 2 false positive, 3 false positive, 4 false positive, 5 false positives, all the way up to 100. That could be a lot of work, all right? So anytime that you have a question that says, and it only works for at least one, okay, remember the probability of at least one is the only time you can use 1 minus the probability of none. So let's do that, because all of those adding up, probability of 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 100, that's all of the probabilities except for the probability of no false positives. Okay, so what is the probability that I get a positive result given that I have a normal pregnancy, and that's 0.05? Okay, what's the probability that I'm going to get a positive result and I'm going to get an abnormality, that's 0.95. So the probability of at least one false positive is 1 minus the probability of none. So what is the probability that I'm going to get no false positives? That's your 0.95 raised to the 100. So 1 minus 0.95 raised to the 100, because 100 of those are going to have no false positives, equals 0.994. Okay, so there's a 0.994 probability that at least one of the 100 women with normal pregnancies will receive a false positive on the first trimester screen. Okay, so go ahead and try this one. So on a recent day, the Arizona Daily Star forecasted 50% chance of rain in the Oro Valley and a 50% chance in rain in Marana. What is the probability it will rain in both locations? Okay. Now, you'll have to recognize that they're independent, since one city does not affect the other city in terms of weather. So, the clouds are where they are, what they're going to do. It doesn't matter, one city is not going to make it rain while the other city is going to make it shiny or sunny. If we could do that, there'd probably be somewhere in the world it was always sunny. Unless you've seen the TV show It's Always Sunny in Philadelphia. Okay, so what exactly is the probability that it's going to rain in both? Since it's independent, you're just going to multiply the two together. 0.5 times 0.5 gives us 0.25. All right, just make sure for your homework and the AP exam that you just show your work. So nothing major, just the probability statement, your multiplication, and the final answer. Go ahead, and I'd like you to try this one on your own before we take a look at the answers. So many employees require prospective employees to take a drug test. A positive result on this test indicates that the prospective employees use illegal drugs. However, not all people who test positive actually use drugs. Have you ever heard of, it's not sesame seeds, one of the seeds I know that can sometimes produce a false positive. Suppose that 4% of prospective employees use the drugs. The false positive rate is 5%, and the false negative rate is 10%. Okay, so the false positive rate means it is positive even if you don't use drugs, and the false negative is that it turns out negative and you do use drugs. So what percent of prospective employees will test positive? Now you're going to decide, are you going to do this using a tree diagram? Are you going to do this just by simply multiplication, two-way table? So think about it, and then we'll take a look at the answer. Okay, so hopefully before we go on to the next slide, you guys all decided that you're going to use a tree diagram. Why would I use a tree diagram? The reason that you're going to reuse a tree diagram is you got two things going on. You're talking about prospective employees using drugs, so using drugs, not using drugs, and then you're talking about a drug test. So I have two things: using drugs, not using drugs, and using a drug test in order to tell whether or not they use drugs. What's our tree diagram going to look like? All right, so you have two things, so you basically have two major branches. So what's the first thing? All right, since the first thing that we want to decide is whether they use drugs or they don't use drugs. So our prospective employees, we know that 4% do use drugs and 96% don't use drugs. So because they have to add up to 1, you do 1 minus to get the 96%. All right, then what else do we know? We know that you get a false positive 5% of the time. Well, what does that tell us? A false positive 5% of the time tells us that if I don't use drugs, it's going to turn up positive 5% of the time. So how can I fill in this branch down here? So it's going to turn up negative 95% of the time when I don't use drugs. Okay, so that's this portion right here. Now, we also know that if you take drugs, it's going to turn up negative, so that's a false positive. that's saying that you didn't use drugs when you actually did. So it's going to say negative when you actually did 10% of the time. So what percent of the time when you use drugs is it going to turn up positive? 90% of the time. All right, because this branch has to add up to 1, this branch has to add up to 1. So you can find those probabilities very easily by subtracting. All right, so the next thing you want to do is always multiply across your branches. Okay, so this tells us we took drugs, positive 0.036% of the time. Took drugs, negative 0.004% of the time. Didn't take drugs, turns up positive 0.048. Didn't take drugs, turns up negative 0.912. All right, so the question is, we want to know what is the probability that the test is going to turn up positive. Well, if you take a look at my tree diagram, there are 2 places it's going to turn up positive. That's if you took drugs and it turned up positive, and you didn't take drugs and it turned up positive. So you have to add that 0.036 to the 0.048. Okay, when you add those 2 together, you get 0.084. This would be difficult to do without the tree diagram. So please, if you got 2 things going on, draw the tree diagram, label all the branches with the probabilities, get the end of the branches, and then look and see what your question's asking. Okay, so what percent will test positive? Add up the ends of the branches for testing positive. So question B is asking what percent of prospective employees will test positive actually use illegal drugs? So what percent of prospective employees who test positive actually use illegal drugs? Okay, now you're going to have to think about, this is 2 things going on. Is this a conditional probability? Is it not? How do I know what the denominator is? Okay, so let's take a look at this. What percent of prospective employees who test positive actually use illegal drugs? So here are a percent of employees that actually test positive. Okay, so the tree diagram is going to help us for it. This is a conditional probability, but once again, notice that we didn't use the word given. You're going to have to think about what was given. What do we already know? We already know that they tested positive. Okay, what percent of prospective employees who test positive? Okay, so remember back to those couple words we talked about, who test positive, that's what we already know actually use illegal drugs. So now I can write my conditional probability correctly. So we already know that they tested positive, that's the given. So what's the probability that they took drugs given that they tested positive? So our conditional probability formula is both combined, drugs and positive over what was given, probability of positive. So once again, tree diagram makes it super easy. Drugs and positive, boom, that's your 0.036 down here. Positive, okay, 2 different times where they are positive. We're going to add that for the denominator. Here's my fraction, that's a decimal, and my final answer. This would be very difficult to do without that tree diagram. 2 things going on, draw the tree diagram. Thus, 42.9% of prospective employees who tested positive actually took the drugs. Venn diagram practice, so go ahead and take a second and look at this one, and we'll go over the answer in about 30 seconds. Okay, so I'm going to go over the answer. If you need to, go ahead and press pause and finish the question before you take a look at the answer. All right, so making a Venn diagram showing the probabilities. Please make sure that you always, hopefully you have this down by now, that you're going to show the and probability first. Okay, so 40% of the students favor the resumption of the military draft for young men, that's our M, 35% for women, and 55% favor neither proposal. Okay, so this is a little tricky. All right, so let's do this. Here's where we had to start first. There was no and section here, so that's a little bit tricky. So there could possibly be an overlap, so we need to make sure that we don't just fill in the women as 35% and the men as 40%. So we know that this one here is 55%, okay? Now, what do I know from that information? If 55% favor neither, then I know that between the men and the women have to favor 45% because that favor neither or favor, so favor plus neither favor has to add up to 1. So I know this entire Venn diagram has to add up to 1. So 0.45 plus 0.55 adds up to 1. But if you look, the 40% and the 35% are definitely bigger than 45%. That's 75%. So how did I get that answer? 1, start with the 55% favor neither. That's on the outside. 2, since we know that the probability that they favor neither, so this is men complement and women complement, okay, so that's your 55%, then we know that men or women is 45%. Okay, so they favor men or women, that's 45%. This is saying the complement of favoring neither is 45. This means that the total inside the circles must add up to 45%. So how can we do that? Oh, let's find our OR rule for the intersection. So the probability that they favor men or women is the probability of men plus the probability of women minus the intersection. And if the intersection is 0, it doesn't matter. That will just end up being 0. Okay, but I know that men or women is 45. I know that men is 0.35, women is 0.4, and I'm going to subtract what's the intersection is. So let's find out the intersection. Okay, that turns out to be 0.3, so now I can fill that in, and the rest is easy. I know this has to be 35, so 35 minus 0.3. I know this has to be 40. 40 minus 0.3 gives me my 0.1. Okay, so let's take a look at our Venn diagram and get a little bit of practice. All right, so A, what is the probability that we're going to favor a draft of young women if it's known that he or she favors a draft for young men? All right, so how could I write that as a conditional probability? So I know it's a conditional probability because it's known that he or she favors a military draft for young men. So the probability that I'm going to favor a draft for women given the fact that I favor a draft for men. All right, so formula, women and men, all over the probability of men. So women and men, easy, 0.3 for my Venn diagram. Okay, men, that's the whole men category, so that's 0.4. Do your division, 0.75. Okay, what is the probability that will favor a military draft of young men if it's known that the student opposes any kind of draft for young women? So our conditional probability is knowing the given is that they oppose any draft for young women. So take a look at our notation that we have here. So the probability that they favor a draft for men given women complement. So what's that women complement mean? It means that they don't favor a draft for any of the women. Okay? So what does my conditional probability look like? The probability that you have men and not women. Okay, so I don't favor the draft for women all over the probability that I don't favor the draft for women. So let's take a look. What is the probability that I don't favor the draft for women? Well, the probability of favoring the draft for women is 0.35. So favoring the draft for women is 0.35. What's not women, so it's everything on the outside here, that's going to be 0.65 or 1 minus 0.35. Okay, so what's the probability? Where's the intersection of men and not women? Okay, so the intersection of men and not women is this area over here. So that's your 0.1. So 0.1 divided by 0.65 gives me 0.153. Okay, show this work, this, and then make sure you get this probability statement correct. All right, last question. Letter C says, what's the probability you'll oppose a service draft for young men if it's known that the student favors a military draft for young men? Sorry, oppose a service draft for women if you know you favor a military draft for young men. Okay, so let's take a look at this. So what's the probability? We know that they favored a military draft for young men, so that's our given. Okay, what's the probability that they'll oppose a service draft for women? So this is favoring a service draft for women, so the complement is not favoring a service draft for young women. So women complement means not favoring a service draft for women is equal to the probability of opposing a service draft for women and favoring it for men all over the probability of favoring it for men. Okay, so the probability of favoring it for men, that's our easier one. So that's this whole thing right here, that's 0.4. So where is the intersection of opposing it for women and favoring it for men? So opposing it for women is outside. Okay, that's would be everything outside here. But and favoring it for men would be right here, this section of 0.1. So 0.1 over 0.4 is 0.25. Okay, these can be a little bit tricky. So
every problem is just a little bit different.
So what's the best way to get better? Practice, practice, practice. There are a ton of practice problem sets. Please make sure that you try them before you're turning in your homework or taking the unit exam. I also cannot stress using your tree diagrams when you have more than one probability going on. Okay, so what did we learn? We calculated and interpreted probabilities. We used the general multiplication rule. We used tree diagrams, which is really important. We determined if two events are independent, and when appropriate, we use the multiplication rule for independent events. So go out there and get some practice with your probabilities.